In this section, we're going to take a look at how we can actually start to synthesize carbohydrates. Now, nature does this very well. Our bodies do this on a daily basis, and yet we are talking about organic chemistry, and therefore we're going to focus our attention on how chemists can actually create new carbohydrates. And in general, there are two main pathways that lead to the formation of new carbohydrates. The first pathway is called the Kiliani-Fischer synthesis. So this is a synthesis. Obviously, Emil Fischer was involved in this synthesis, along with I think this was a student of his, Kiliani. And essentially, this type of synthesis, the important thing to understand is this type of synthesis increases the carbon chain, and therefore we're going from, let's say, an aldottetros to an aldopentose, or an aldopentose into an aldohexose. So we're increasing the carbon chain by one carbon. And then, of course, if we can increase the chain, we can also decrease the chain in a process called the rough degradation. We're degrading a carbohydrate, and in this process, we're losing one carbon. We're decreasing the chain length of the particular carbohydrate. Right. So let's take a look at these kind of separately. Obviously, we'll take a look at the Kiliani-Fischer synthesis, and there really isn't any new chemistry with the Kiliani-Fischer synthesis. You simply have to understand how the chemistry is being used and the result of them, right? So the first thing we do in a Kiliani-Fischer synthesis is we make the cyanohydrin. We have an aldehyde, we can treat it with sodium cyanide in water, and we get a cyanohydrin. And then what we're going to see is we're going to reduce the cyanide, the nitrile, to an imine. So this is going to involve the reduction of a triple bond into a double bond. And so we're going to have to use a poisoned catalyst in that type of reaction. And then once we have an imine, we know that imines can be hydrolyzed to aldehydes or ketones, and that's exactly what we're going to do. We're going to hydrolyze the imine to the aldehyde. So as an example, I'm going to take a tetros here, an aldotetros. You should think about how to name this aldotetros. One of the things, you should be able to name the aldotetroses. There's really only two of them. There's erythros and threose. This happens to be erythros, and of course we see that the configurational carbon has OH on the right, so this is D-erythros. And what we can do with D-erythros, as we can do with all of the sugars, is we can treat this with sodium cyanide in water. And so what's going to happen? The cyanide is going to attack the aldehyde, and so we get an OH and a cyanide and a hydrogen coming off of that carbon. So when we draw this, of course, notice the stereogenic centers, stereogenic carbons haven't changed. There's no stereochemistry taking place. The reaction is taking place at the aldehyde carbon. And so a cyanide comes in. We typically are going to draw that cyanide on the top. Why? Because the other substituents are an OH group and a hydrogen. Well, how can the OH group and the hydrogen be oriented? One, the OH group could be on the right-hand side and the hydrogen can be on the left-hand side. Or we can also produce the diastereomer where the OH is on the left and the hydrogen is on the right. Right? So we're going to be producing these two structures, these two molecules. Now, I'm going to clean this up a little bit, and so now notice I have created a new stereogenic center of that carbon on the top there, that is the cyanohydrin is now a stereogenic center. So I'm now going to incorporate that into a new Fisher projection. I'm going to redraw it. So now I have 3 stereogenic centers. And of course I could draw it, and notice the most oxidized carbon, the nitrile, is drawn on the top, CH2 is drawn on the bottom, and so I could draw it with the OH on the right hand side, or I could draw it with the OH on the left hand side, right? So these are the 2 diastereomers that I get. They are diastereomers of one another. They happen to be called, well, their sugars happen to be called epimers of one another. And now I want to reduce the nitrile, but I don't want to reduce it to an amine. I want to reduce it to an imine. So I only want to reduce one of the pi bonds. I don't want to reduce both of them. How do I do that? Just like with alkynes, we can selectively reduce them to alkenes if we use hydrogen over a poison catalyst. And the typical poison catalyst is the Lindlar catalyst, Lindlar palladium. Then we can reduce the nitrile to an imine, and so we get structures that look like this. So now that nitrile is an imine, so it has a hydrogen coming off of the carbon, and then that double bonded NH group. And of course, I'll get a product for each one of them, an imine product for each one of them, which I'm drawing right here. So now I have the 2 imines, and generally speaking, those imines aren't isolated at all. We're going to simply go ahead and we're going to hydrolyze them with water in some acidic conditions, and now the imine gets converted into a carbonyl, and so we get an aldehyde, and the structures look like this. So this is one sugar, 1 carbohydrate, where now I have an aldehyde. Notice a new aldehyde, and I've added on a carbon, so now I have 3 stereogenic centers. And of course, I'm also going to get its epimer, where the OH that on that C, now new C2, is on the left-hand side. With its aldehyde. So notice again, though, the configurational carbons both have the OH groups on the right hand side. So these are the D carbohydrates. The one on the left hand side there is ribose. Again, you should at least know ribose. That's very important in DNA synthesis. And the one on the right hand side is D-arabinose. So D-ribose and D-arabinose are referred to as epimers of one another because their C2 carbons are opposite one another, basically. So that is the Kiliani-Fisher synthesis. We essentially have added a carbon, and we take one carbohydrate. We end up getting 2 carbohydrates that are epimers of one another. The second reaction is called the rough degradation. And in general, what we're going to be doing here is we're going to oxidize the aldehyde to a carboxylate salt, so a carboxylic acid salt, and then we're going to decarboxylate that carboxylic acid, and in the process we're going to oxidize what was C2 now into an aldehyde. So in terms of the reagents, we're going to take a look at, here is an aldohexose. You should by now be a little bit familiar with this particular structure. Obviously this is D-glucose. So now how do we oxidize an aldehyde without oxidizing? There's a whole bunch of alcohols there, right? And we've seen that when you oxidize an aldehyde, most of the time you're going to oxidize alcohols. So what happened is that Rough developed a way of selectively oxidizing an aldehyde. And he found out that you only need a mild oxidant to oxidize an aldehyde to a carboxylic acid, and in the process keep the alcohols as alcohols and not oxidize them. And the way he did this was with bromine and water. So bromine is an oxidant, and it can oxidize an aldehyde into a carboxylic acid in general. So every once in a while you'll see this selectively being used, bromine, water. It's kind of an odd thing to think about. And of course, this is followed by a basic workup with something like calcium hydroxide. So what you end up getting is now the aldehyde has been oxidized into a carboxylate. And of course, you know, there's a cation around. Obviously, the only cation is calcium, and I know that the charges don't add up here, but this is typically the way that it is written. So probably for every one calcium ion, there are two of these oxidized sugars that are in solution, obviously. But again, notice that the stereogenic carbons haven't been touched yet. So now what's going to happen in the second stage is that we're going to decarboxylate that top carbon. So C1 is going to come off, and C2 is going to selectively be oxidized to an aldehyde. Again, after much fiddling, chemists figured out that if they take ferric sulfate in water at 100 degrees, you can decarboxylate and then treat with 30% hydrogen peroxide. This is concentrated hydrogen peroxide. And you oxidize that C2 carbon selectively, which is kind of a cool thing. The mechanism of this obviously is not known, so we don't really have to worry about it. But again, when we think about the stereochemistry of the remaining three carbons, we see that the stereochemistry of the configurational carbon hasn't changed, and the other two carbons haven't changed. And so now that what was now C2 is C1, and it is an aldehyde. And so we've basically taken D-glucose and we've converted it. We've gone from an aldohexose sugar into an aldopentose sugar, which is D-arabinose. So converting D-glucose into D-arabinose. And essentially you can now start to envision that Fischer basically took sugars and either added things or took them off to essentially now categorize other sugars from only a select few number of sugars. And so that's kind of a key aspect in terms of carbohydrate chemistry. How do we build, how do we manipulate sugars, how do we add carbons, how do we take carbons off? And then later on we're going to see how do we protect one, certain alcohol functional groups over other alcohol functional groups.